Light never rests, never pauses, never slows down, not even for a moment. Every photon that has ever existed, from the first glow of the universe to the gentle light touching your face right now, moves at exactly the same relentless speed through space. Tonight we'll explore why this must be so, step by step, using the quiet mathematics of mass, energy, and the fabric of space-time itself. It's a story written in the language of physics, where having no rest mass becomes not a limitation, but a kind of cosmic freedom, precise, inevitable, and surprisingly gentle. We'll discover how Einstein's equations reveal that for light to exist at all, it must always be in motion, forever travelling at nature's ultimate speed limit. If this peaceful journey through the physics of light helps you unwind or satisfies your curiosity, your thoughtful like, your quiet subscription, and any comments you share mean the world to me. Let's begin this exploration together, moving as steadily as light itself. Have you ever wondered why the moment you flip a switch, light instantly fills a room, as if it was somehow always ready, always waiting to rush forward at precisely the same speed every single time? Hello there, and welcome to Science for Sleep, where we explore the gentle mysteries that surround us each day, allowing complex ideas to unfold naturally as your mind settles into a peaceful state of curiosity. Tonight we embark on a journey to understand something quietly extraordinary about light itself, something so fundamental that it shapes every moment of illumination you experience, from the soft glow of your bedside lamp to the ancient starlight filtering through your window right now. Can you sense the gentle warmth of whatever light source accompanies you this evening? Perhaps a reading lamp casting its steady beam, or moonbeams drawing silver patterns across your walls, or even the subtle luminescence from a distant streetlight painting soft shadows in your room. Each photon reaching your eyes carries within it a profound secret about the nature of reality, a secret that connects the smallest scales of quantum mechanics to the grandest structures of our universe. What if I told you that every single particle of light that has ever existed, from the first brilliant flash of cosmic creation to the gentle radiance illuminating these words, has never once slowed down, never paused, never rested for even the tiniest fraction of a second? This eternal dance of photons reveals something beautiful about the mathematical elegance underlying our physical world, something that Einstein himself marveled at when he first glimpsed the deeper connections between energy, mass, and the fabric of space-time. If this peaceful exploration brings you new understanding or simply helps your thoughts drift into calmer waters, your gentle engagement through a like, your quiet subscription, and any reflections you choose to share create a wonderful community of curious minds seeking knowledge in the most restful way possible. Tonight we begin CS by observing something you encounter countless times each day but yet might never have questioned deeply, this instantaneous response of light that seems to bridge any distance in your immediate environment without delay. Why does light behave this way while everything else we know can slow down, speed up, or come to rest? What makes electromagnetic radiation so uniquely different from matter, from particles that can be caught, held, and studied in stationary states? The answer lies hidden in the deepest principles governing our universe, principles that reveal themselves through patient observation and gentle mathematical reasoning. We will move slowly through these concepts, allowing each idea to settle comfortably before building upon it, recognizing that understanding emerges not through force, but through quiet contemplation. Consider how light travels from distant galaxies across billions of years, maintaining its unwavering velocity through the vast emptiness of space, carrying information about stellar births and deaths, chemical compositions, and cosmic events that occurred long before Earth even existed. This same light that illuminates nebulae and reveals the structure of our expanding universe operates under identical principles as the modest illumination surrounding you now. Every photon shares this remarkable property of eternal motion, whether it emerge from nuclear fusion in stellar cores, fluorescent tubes in your ceiling, or light-emitting diodes in electronic displays. There exists a profound unity connecting all these sources, a unity rooted in the fundamental nature of what light actually represents in the grand symphony of physical forces. As we explore together why photons can never stop moving, we will discover how this seemingly simple fact connects to some of the most elegant mathematical structures in all of physics, structures that govern everything from the conservation of electric charge to the shape of atoms themselves. The masslessness of light particles turns out to be not merely an interesting property, but an absolute necessity, required by the very symmetries that allow our universe to function coherently. Through gentle steps, we will see how special relativity, quantum field theory, and geometries all converge on this same beautiful conclusion that light must forever move at exactly one speed, never faster, never slower. Let yourself relax into this exploration, knowing that complex ideas become clearer when approached with patience and wonder rather than urgency. What invisible force compels every beam, ray, and glimmer surrounding you at this very moment to maintain exactly the same relentless velocity, never varying by even the smallest measurable amount? The electromagnetic radiation streaming from your reading lamp, the ancient starlight that began its journey millions of years ago, the gentle glow from your phone, screen, and even the infrared heat radiating from your own body all participate in this cosmic choreography, moving through space at precisely 292,158 meters per second without exception. How extraordinary that whether we examine photons born in the nuclear furnaces of distant suns, or those emerging from the humble filament of an incandescent bulb, each one travels at this identical speed, as if obeying some fundamental law that permits no deviation whatsoever. This universal constant represents something far deeper than mere measurement, something that reveals the very architecture of reality itself, where electromagnetic phenomena operate according to principles so basic that they shape the structure of atoms, molecules, and all the matter composing our physical world. Consider the remarkable phenomenon you witness each time you activate a light switch, how illumination appears to fill your entire room instantaneously, reaching every corner and surface without any perceptible delay. What mechanism allows this near instantaneous flooding of brightness to occur so reliably, creating the illusion that light somehow exists everywhere simultaneously, waiting to be released? The truth reveals something even more fascinating than instant appearance, for these photons actually traverse the distance from source to destination, covering the span of your room in approximately 10 nanoseconds, a duration so brief that our senses cannot distinguish it from simultaneity. This blazing swiftness emerges not from some special acceleration process, but represents the natural state of electromagnetic radiation, the only velocity at which photons can exist in our universe. Why should this be so, when virtually everything else we encounter in daily experience can slow down, speed up, or remain motionless relative to our reference frame? Automobiles cruise at various speeds and park in driveways, airplanes accelerate down runways and taxi slowly to gates. Even subatomic, particles like electrons can be slowed, stopped, and trapped in carefully designed experimental apparatus. Yet photons seem exempt from this flexibility, forever locked into their cosmic velocity as if motion itself were their essential nature, rather than simply something they happen to be doing. This peculiar behavior hints at something profound about the relationship between light and the fundamental structure of spacetime, something that connects the smallest quantum interactions to the largest cosmic phenomena through mathematical elegance and physical necessity. The electromagnetic spectrum encompasses far more than visible illumination, extending from radio waves with wavelengths measured in kilometers down to gamma rays with wavelengths smaller than atomic nuclei, yet every form of this radiation travels at identical speed, regardless of frequency or energy content. Radio signals carrying music to your receiver, microwaves heating food in kitchen appliances, X-rays revealing internal structures in medical imaging, and ultraviolet radiation from our sun all participate in this same unwavering march through space at light speed. What unifying principle could possibly govern such diverse phenomena, ensuring that despite their vastly different properties and applications, they all obey this single constraint on velocity? The answer emerges from recognizing that all these seemingly different forms of radiation represent variations of one underlying phenomenon, oscillating electric and magnetic fields propagating through the vacuum of space according to the elegant equations Maxwell derived in the 19th century. These mathematical relationships predicted the existence of electromagnetic waves traveling at a specific velocity determined by fundamental constants of nature, constants that describe how electric and magnetic fields interact with the fabric of space-time itself. There exists no mechanism by which these waves could travel faster or slower while maintaining their essential electromagnetic character, for their speed emerges directly from the properties of empty space and the way energy propagates through it. As we continue exploring together, there is no need to hurry through these concepts, for understanding develops naturally when we allow ideas to resonate and connect with our intuitive experience of the physical world. Let your mind drift gently between the immediate reality of illuminated surroundings and the deeper principles governing how that illumination reaches you, appreciating both the practical familiarity and the underlying mystery of light's eternal journey through our universe. What makes certain scientific discoveries simultaneously elegant in their simplicity and profound in their implications for understanding the deepest workings of our universe? Tonight we embark upon an exploration that begins with observations as familiar as flipping a switch or watching sunbeams stream through windows, yet gradually reveals connections to some of the most fundamental principles governing reality itself. How remarkable that something as commonplace as the glow from your bedside lamp connects directly to Einstein's revolutionary insights about space and time, to the quantum mechanical nature of energy and matter, and to the mathematical symmetries that ensure our universe operates coherently across all scales from subatomic to galactic. There is something beautifully reassuring about allowing these ideas to settle gently in your consciousness without pressure to grasp everything immediately, recognizing that genuine understanding often emerges through patient contemplation rather than forced concentration. As we move forward together, we will trace a path from household illumination to cosmic radiation, from everyday electrical devices to the fundamental forces that bind atoms and enable chemistry itself to function. Why does this journey from mundane to magnificent feel so natural, so inevitable, once we begin following the threads of inquiry that light itself provides? The answer lies in recognizing that scientific understanding often works this way, revealing how apparent complexity dissolves when we discover the underlying simplicity of natural laws, while simultaneously showing how simple phenomena connect to profound truths about the structure of existence. Our route will lead us through several connected territories of knowledge, each building, naturally, upon the previous while maintaining its own intrinsic beauty and significance. We will explore what light actually represents at its most fundamental level, examining how electromagnetic radiation emerges from the interplay between electric and magnetic fields, oscillating through space according to precise mathematical relationships. What transforms these abstract field equations into the concrete experience of brightness filling your room when you activate a lamp, or warmth reaching your face from distant stellar fusion? Reactions? Through gentle steps, we will investigate the concept of mass itself, discovering how modern physics distinguishes between the mass objects possess when at rest and the more complex relationships that emerge when things move at high velocities approaching the speed of electromagnetic radiation. How does Einstein's famous equation E equals mc squared fit into this picture? And why does the complete energy-momentum relationship reveal even deeper insights about the nature of massless particles like photons? We will encounter the elegant mathematical structures called gauge symmetries that govern electromagnetic interactions, learning how these abstract principles require photons to remain forever massless and thus forever moving at light speed. What mysterious connection exists between the conservation of electric charge, the mathematical consistency of electromagnetic theory, and the inability of light particles to ever slow down or come to rest? These questions guide us toward understanding how the universe maintains its coherent structure through fundamental symmetries that operate whether we are examining interactions between electrons in copper wires or the propagation of radio signals across intergalactic distances. The experimental evidence supporting these theoretical insights spans nearly 2 centuries of scientific investigation, from Maxwell's original predictions about electromagnetic waves to modern attempts to measure any possible mass that photons might possess. Why have all such measurements consistently found that photon mass, if it exists at all, must be so incredibly tiny as to be essentially zero for all practical purposes? We will discover how this experimental confirmation connects to broader themes about the relationship between mathematical beauty and physical reality, exploring how abstract theoretical principles often guide us toward concrete discoveries about the natural world. Throughout this expedition through ideas and evidence, we have all the time we need to let each concept develop naturally, to appreciate both the logical progression and the moments of wonder that arise when disparate pieces of knowledge suddenly click into place. What makes this unhurried approach so effective for absorbing complex information about topics ranging from quantum mechanics to cosmology? Perhaps it reflects something fundamental about how human understanding actually develops, through gradual accumulation of insights rather than sudden revelations, through patient observation rather than hasty conclusions. The beauty of exploring why photons can never stop moving lies not just in reaching the final answer, but in appreciating how that answer emerges from the intersection of multiple scientific disciplines, each contributing essential pieces to our overall comprehension of electromagnetic phenomena and their role in shaping our universe from its smallest to its largest scales. Have you ever paused to consider why morning sunlight appears to arrive at your window the very instant dawn breaks, as if the entire 93 million mile journey from our star's surface somehow compressed into a moment of pure illumination? Each day we witness countless examples of electromagnetic radiation behaving in ways that seem almost magical in their immediacy. From the instant brightness that floods your bedroom when you flip the bedside switch to the immediate glow that emanates from your phone screen, the microsecond pixels receive their electronic signals. What invisible choreography orchestrates these phenomena so that artificial and natural luminosity alike respond with such apparent instantaneousness to their triggering events? The golden rays streaming through your morning window began their existence deep within the solar core, where hydrogen nuclei fuse under tremendous pressure and temperature to create helium, while releasing pure energy in the form of gamma radiation. These high-energy photons then embark on a remarkable odyssey, bouncing randomly through the dense solar interior for thousands of years before finally escaping the sun's surface and racing across the vacuum of interplanetary space at nearly 300,000 kilometers per second. Why does this 8-minute journey from solar surface to Earth feel instantaneous to our human perception, creating the illusion that sunrise occurs simultaneously with the appearance of brightness in our terrestrial environment? The explanation lies in recognizing how our biological sensory apparatus evolved to function within a world where electromagnetic signals travel so rapidly that delays become imperceptible except across astronomical distances. Consider the remarkable responsiveness you experience when activating any electrical lighting device, how the tungsten filament in an incandescent bulb begins emitting visible radiation. Seemingly the same instant electrical current flows through its resistive element. What mechanisms enable this apparently immediate transformation from electrical energy to luminous output, creating the impression that illumination simply materializes wherever you direct it? The tungsten atoms within the filament begin vibrating more vigorously as electrical current increases their thermal energy, causing them to emit electromagnetic radiation across a spectrum that includes substantial visible wavelengths. But the photons themselves still require finite time to travel from their source to your retinas, even though that duration measures only nanoseconds across typical room dimensions. Automobile headlights cutting through nighttime darkness demonstrate another fascinating example of light's apparent immediacy. How the beam seems to instantly project forward the moment you engage the switch, revealing road surfaces, signs, and obstacles that were previously invisible. How do these concentrated streams of photons manage to maintain their coherence and intensity while propagating through air filled with dust particles, water vapor, and countless other microscopic obstacles that might scatter or absorb the radiation? The answer involves understanding how electromagnetic waves interact with matter much smaller than their wavelengths, generally passing through such particles with minimal deflection, while occasionally encountering larger objects that create the visible scattering effects we observe as haze or atmospheric perspective. Digital screens surrounding us in modern life provide perhaps the most striking examples of light's apparent instantaneity. How liquid crystal displays, organic light-emitting diodes, and plasma panels can alter their luminous output faster than human vision can detect individual changes. What technological marvels enable these devices to modulate millions of tiny light sources with such precision and speed that moving images appear smooth and continuous, rather than flickering or stuttering? Each pixel represents a carefully controlled electromagnetic emitter capable of adjusting its spectral output thousands of times per second, yet the photons emerging from each microscopic element still obey the same fundamental velocity constraint that governs stellar radiation and domestic illumination alike. The glow reaching your visual system from any electronic display began its journey mere nanoseconds earlier at the screen surface, travelling through air and the transparent structures of your eyes before striking photoreceptive cells in your retina and triggering the neural cascades that create conscious visual experience. Why do all these diverse sources of electromagnetic radiation, despite their vastly different origins, mechanisms, and purposes, share this common behaviour of propagating at identical velocity through space? Television broadcasts, wireless internet signals, garage door openers, and medical X-ray machines all employ electromagnetic radiation operating at this same fundamental speed, suggesting some deeper principle governs all such phenomena regardless of their practical applications or energy levels. The unity underlying these apparently different technologies points toward universal laws that constrain how energy and information propagate through our physical universe, laws that we will explore more deeply as our investigation continues into the quantum, mechanical, and relativistic foundations of electromagnetic behaviour. What cosmic boundary determines the maximum velocity at which any information, energy, or causal influence can propagate through our universe, establishing an absolute limit that nothing material can ever exceed? The electromagnetic radiation surrounding you at this moment travels at approximately 458 meters per second, a velocity so extraordinary that if a photon could somehow circle Earth's equatorial circumference, it would complete 7.5 such journeys in a single second, while maintaining perfect precision in its orbital path. How did nature settle upon this particular numerical value for what physicists call the fundamental constant C, and why does this specific rate of propagation appear to govern not just electromagnetic phenomena, but the very structure of space-time itself? This remarkable velocity represents far more than simply how fast light moves, for it establishes the universal speed limit that constrains all physical processes, from the strongest nuclear interactions to the weakest gravitational effects across galactic distances. Consider how this cosmic velocity translates into your immediate environment, where photons from your reading lamp traverse the modest distance to your eyes in approximately 10 nanoseconds, a duration so brief that even our most sophisticated timing instruments struggle to measure such intervals with precision. What does it mean that every electromagnetic interaction in your vicinity, from the radio waves carrying broadcast signals to the infrared radiation warming your skin, operates according to this identical temporal constraint? The universality of this speed limit reveals something profound about the mathematical architecture underlying physical reality, suggesting that space and time themselves possess inherent properties that determine how quickly changes can propagate from one location to another. Radio telescopes detecting signals from distant galaxies observe electromagnetic radiation that has maintained this exact same velocity throughout journeys lasting billions of years, crossing virtually empty intergalactic space while carrying information about stellar formations, cosmic explosions, and the large-scale structure of our expanding universe. Why should radiation emitted by exotic astronomical objects like pulsars, quasars, and gamma-ray bursts travel at precisely the same rate as the modest illumination from household fixtures, despite originating under conditions of extreme temperature, pressure, and magnetic field strength? This constancy suggests that the speed of electromagnetic propagation represents not merely an average or approximate value, but an absolute requirement built into the fundamental laws governing how energy and information move through the cosmos. The precision with which this velocity maintains its value becomes even more remarkable when we consider the vast range of conditions under which electromagnetic radiation operates, from the near-absolute zero temperatures of deep space to the million-degree plasmas surrounding massive stars. What physical mechanism ensures that photons emerging from such dramatically different environments all travel at identical speeds, regardless of their energy content, frequency, or the circumstances of their creation? The answer points towards something even deeper than electromagnetic theory alone, connecting to the very geometry of space-time and the way that mass, energy, and momentum relate to each other through Einstein's revolutionary insights about the nature of physical reality. Experimental measurements of this fundamental constant have achieved extraordinary precision through increasingly sophisticated techniques, confirming that the speed of electromagnetic radiation remains stable across all observable scales and timescales, from laboratory experiments lasting microseconds to astronomical observations spanning cosmic epochs. How do scientists manage to verify this constancy with such confidence? And what would happen to our understanding of physics if even tiny variations were discovered in different regions of space or different moments in cosmic history? The implications extend far beyond electromagnetic theory, for this velocity appears in the fundamental equations describing nuclear forces, gravitational interactions, and even the quantum mechanical behavior of subatomic particles, suggesting its truly universal significance. Modern technology depends critically upon this constancy, from global positioning satellites that require precise timing to synchronize their signals across orbital distances, to fiber optic communications that rely on predictable propagation delays through crystalline waveguides stretching across continents. What would happen to our interconnected technological civilization if the speed of electromagnetic radiation suddenly began fluctuating or varying with location? And how do we know with such certainty that such variations do not occur? The mathematical elegance of this universal constant extends beyond its numerical value to encompass its role in connecting space and time into a unified four-dimensional structure, where intervals between events remain invariant despite different perspectives from various observers moving at different velocities relative to each other. What fundamental principle distinguishes electromagnetic radiation from every other form of matter and energy we encounter, making it uniquely incapable of slowing down, speeding up, or achieving a state of complete motionlessness? Consider how easily we can bring familiar objects to rest relative to our reference frame, from automobiles coasting to a stop at traffic signals, to aircraft landing and parking at airport gates, from flowing rivers freezing into solid ice to electrons trapped within carefully designed electromagnetic confinement systems in laboratory experiments. Why does photonic radiation seem exempt from this universal ability to transition between motion and stillness, forever locked into its cosmic velocity regardless of the circumstances surrounding its creation or propagation? Even subatomic particles like protons, neutrons, and electrons can be slowed through electromagnetic fields, captured in magnetic bottles, or cooled to near absolute zero temperatures where their kinetic motion approaches zero. Yet electromagnetic quanta appear immune to any such manipulation or control. What makes these packets of radiant energy so fundamentally different from material particles that they cannot participate in the ordinary transitions between movement and rest that characterize virtually every other physical phenomenon? The mystery deepens when we realize that electromagnetic radiation can be absorbed, reflected, refracted, and even converted into other forms of energy, suggesting it does interact with matter in predictable ways. Yet throughout all these processes, any photons that continue existing maintain their unwavering velocity without deviation. This peculiar behavior hints at something profound about the essential nature of electromagnetic phenomena, something that distinguishes them from material objects not merely in degree, but in their fundamental relationship to space, time, and the structure of physical reality itself. Consider what we actually mean when we describe something as being at rest, for this seemingly simple concept becomes remarkably complex when examined closely through the lens of modern physics and relativity theory. Does an object sitting, motionless on your desk truly qualify as being at rest, given that Earth rotates on its axis, orbits around the Sun, moves through our galaxy, and participates in the cosmic expansion that carries our entire local cluster of galaxies through space-time? The notion of absolute rest proves elusive once we recognize that all motion remains relative to chosen reference frames, yet most material objects can achieve zero velocity relative to any particular observer, while electromagnetic radiation maintains its characteristic speed regardless of the observer's own state of motion. What could possibly account for this asymmetry between matter and radiant energy, this fundamental difference in how they relate to the concept of rest and the possibility of achieving zero velocity? The answer requires us to examine what electromagnetic radiation actually represents at its most basic level, moving beyond our everyday experience of brightness and warmth to investigate the deeper physical processes that create and sustain these phenomena. Light reveals itself to be something far more subtle and complex than our intuitive understanding suggests, emerging from the intricate dance between electric and magnetic fields that propagate through space according to mathematical relationships discovered in the 19th century by James Clerk Maxwell. These field equations predict the existence of self-sustaining oscillations that move through vacuum at a specific velocity determined by fundamental constants describing how electric and magnetic effects interact with the geometry of space-time itself. Why should these abstract mathematical constructs correspond so precisely to the concrete phenomenon of electromagnetic radiation that illuminates our world and enables our technological civilization? The correspondence suggests that our everyday experience of light represents merely the macroscopic manifestation of deeper quantum mechanical processes involving the emission, absorption, and propagation of discrete energy packets called photons. Each photon embodies a specific quantum of electromagnetic field energy, carrying momentum despite possessing zero rest mass, a paradoxical combination that becomes comprehensible only through Einstein's revolutionary insights about the equivalence of mass and energy and the fundamental structure of spacetime. What makes photons so unlike material particles that they can simultaneously carry momentum and energy while maintaining zero rest mass? And how does this unusual combination of properties constrain their behavior in ways that forbid them from ever slowing down or coming to rest? The answer emerges from recognizing that photons represent excitations of the electromagnetic field itself, rather than discrete material objects moving through space, making their relationship to motion and rest fundamentally different from our intuitive expectations based on everyday experience with material objects that can be accelerated, decelerated, and brought to rest through applied forces. What if the continuous beam of light streaming from your reading lamp actually consists of countless individual packets of energy, each one a discrete bundle carrying a specific amount of electromagnetic power through space like tiny messengers delivering their cargo to whatever surface they encounter? This revolutionary insight emerged in the early 20th century when physicists began to realize that electromagnetic radiation, despite appearing as smooth, continuous waves in our everyday experience, actually arrives in distinct, indivisible units called quanta, or photons. How can something that seems so fluid and wave-like as the illumination filling your room actually be composed of separate, countable particles, each carrying its own precise allotment of energy? The answer requires us to embrace one of nature's most beautiful paradoxes, recognizing that electromagnetic phenomena simultaneously exhibit both wave-like and particle-like characteristics depending upon how we choose to observe and measure them. Consider the analogy of water flowing from a faucet, appearing as a steady, continuous stream from a distance, yet revealing itself upon closer inspection to consist of countless individual droplets, each maintaining its distinct identity while contributing to the overall flow pattern. Similarly, the luminous output from any source, whether natural stellar fusion or artificial electrical excitation, emerges as a torrent of discrete photons, each one an elementary quantum of electromagnetic field energy propagating independently through space while collectively creating the impression of continuous radiation. What determines how much energy each individual photon carries as it travels from source to detector, and why do different colors of visible light correspond to different energy contents per quantum? The relationship between photon energy and electromagnetic frequency provides one of the most elegant connections in all of physics, expressed through Einstein's deceptively simple equation E equals h times F, where E represents the energy carried by each photon, H denotes Planck's constant, and F indicates the frequency of the electromagnetic oscillation. This mathematical relationship reveals that higher frequency radiation corresponds to more energetic photons, explaining why blue light carries greater energy per quantum than red light, why ultraviolet radiation can cause chemical reactions that visible light cannot initiate, and why X-rays penetrate materials that completely block lower frequency electromagnetic radiation. How remarkable that this single equation connects the abstract concept of frequency, measured in cycles per second, to the concrete physical quantity of energy, measured in joules, through a fundamental constant of nature that determines the scale at which quantum effects become significant. Planck's constant represents the quantum of action, the smallest possible change in angular momentum that any physical system can undergo, establishing the boundary between classical continuous physics and quantum discrete physics throughout the universe. What makes this constant so special that it appears in virtually every equation describing quantum mechanical phenomena, from the behavior of electrons in atoms to the emission of radiation by heated objects? The answer lies in recognizing that Planck's constant sets the scale at which the granular, particulate nature of energy becomes apparent, below which the smooth, continuous approximations of classical physics break down and reveal the underlying quantum structure of reality itself. Red photons, with their relatively low frequencies around 430 terahertz, carry approximately 2.8 electron volts of energy per quantum, while blue photons, oscillating at roughly 670 terahertz, deliver about 4.1 electron volts per particle, explaining why blue laser pointers can appear brighter than red. Ones of equivalent power output, and why blue light proves more effective at regulating circadian rhythms than red illumination. Infrared radiation, invisible to human vision but detectable as heat, consists of even lower energy photons that can warm surfaces without providing sufficient energy per quantum to trigger the photochemical processes underlying vision in biological systems. What happens when we extend this energy-frequency relationship to even higher frequencies, into the ultraviolet, X-ray and gamma-ray regions of the electromagnetic spectrum? Each step toward higher frequency corresponds to dramatically increased energy per photon, with gamma rays carrying millions of times more energy than visible light quanta, enabling them to penetrate dense materials, ionize atoms, and trigger nuclear reactions that lower energy radiation cannot induce. This progression reveals how the quantum nature of electromagnetic radiation connects directly to its practical effects and technological applications, from the gentle warmth of infrared heaters to the powerful penetrating capabilities of medical imaging systems that rely on high-energy photonic bombardment to reveal internal structures without surgical intervention. How can electromagnetic radiation simultaneously behave as both a continuous wave spreading through space and a collection of discrete particles arriving at detectors, one by one, creating what appears to be an impossible contradiction that challenges our deepest intuitions about the nature of physical reality? This fundamental duality represents one of the most profound mysteries in modern physics, revealing that our everyday concepts of waves and particles provide inadequate frameworks for understanding the true character of light and other quantum phenomena. When electromagnetic radiation encounters narrow slits or small obstacles, it demonstrates unmistakably wave-like behavior by creating interference patterns, alternating bands of brightness and darkness that emerge when waves from different paths combine constructively and destructively, according to their relative phases. What mechanism allows these waves to bend around corners through diffraction effects, spreading into regions that would remain dark if light travelled strictly in straight lines like classical particles? The wave-like nature becomes even more apparent in phenomena such as polarization, where electromagnetic oscillations can be filtered to vibrate in specific directions, and dispersion, where different frequencies propagate at slightly different velocities through certain materials, causing white light to separate into rainbow spectra when passing through prisms or water droplets. Yet this same electromagnetic radiation reveals its particle nature when interacting with individual atoms and molecules, arriving at photodetectors as discrete impacts that can be counted one by one, each carrying a specific quantum of energy determined by Planck's equation relating photon energy to frequency. Why do these individual particle-like impacts collectively reproduce the smooth intensity distributions predicted by wave theory? And how can something be simultaneously continuous enough to create interference patterns, yet discrete enough to trigger individual detector responses? The mystery deepens when we realize that this duality applies not only to electromagnetic radiation but to all quantum objects, including electrons, protons, and even entire atoms under appropriate experimental conditions. What fundamental aspect of nature could possibly account for this universal wave-particle complementarity that appears throughout the microscopic world? The resolution lies not in choosing between wave and particle descriptions, but in recognizing that both represent incomplete classical analogies for quantum phenomena that transcend our everyday experience with macroscopic objects. This duality might feel strange and counterintuitive, and that reaction is perfectly natural given how our brains evolved to understand medium-sized objects moving at moderate speeds rather than quantum entities operating according to probability amplitudes and superposition principles. How do physicists reconcile these apparently contradictory behaviors in their mathematical formulations of quantum mechanics and electromagnetic field theory? The answer involves describing quantum systems using complex mathematical objects called wave functions that encode probability distributions for various measurable properties, allowing the same mathematical framework to predict both wave-like interference effects and particle-like detection events depending upon the experimental setup and measurement procedure. We don't need to fully solve this conceptual puzzle to understand our central question about why photons cannot stop moving. for the essential physics emerges from other considerations related to mass, energy, and the fundamental structure of spacetime itself. What we do need to appreciate is that photons represent genuine quantum objects whose behavior cannot be fully captured by either classical wave theory or classical particle mechanics alone, requiring instead the more sophisticated mathematical machinery of quantum field theory to provide complete descriptions. The wave-particle duality reveals itself most dramatically in experiments where individual photons appear to interfere with themselves, somehow taking multiple paths simultaneously through double-slit apparatus and creating interference patterns even when only one photon at a time passes through the experimental setup. How can a single particle interfere with itself, and what does this tell us about the nature of electromagnetic quanta and their relationship to space and time? These questions lead toward deeper insights about quantum superposition, where particles exist in combinations of multiple states until measurement forces them to assume definite values, and quantum entanglement, where separated particles maintain mysterious correlations that seem to violate our classical understanding of locality and independence. The practical consequences of wave-particle duality permeate modern technology, from laser systems that rely on coherent wave properties to photovoltaic cells that depend on particle-like photon absorption, from fiber optic communications that exploit wave-like propagation through crystalline waveguides to quantum cryptography protocols that utilize the discrete nature of individual photon detections to ensure information security through fundamental physical principles rather than computational complexity. What invisible messengers constantly shuttle between every charged particle in the universe carrying the electromagnetic force that holds atoms together, enables chemical bonds to form, and allows your neurons to communicate through electrical signals racing along nerve pathways? Photons serve as the fundamental carriers of electromagnetic interaction, acting as quantum field excitations that mediate all electrical and magnetic phenomena, from the smallest atomic scales to the largest cosmic structures where magnetic fields shape galactic evolution across billions of light years. How do these massless quanta manage to transmit forces between charged objects separated by vast distances, creating attractions and repulsions that govern everything from the behavior of electrons orbiting atomic nuclei to the operation of electric motors powering industrial machinery? The mechanism involves what physicists call virtual photon exchange, where charged particles continuously emit and absorb electromagnetic quanta in a ceaseless dance of quantum communication that maintains the forces we observe as static electricity, magnetic attraction, and all the complex electromagnetic interactions underlying modern technology. Every time you rub a balloon against your hair and watch it attract small pieces of paper, countless virtual photons are mediating the electrostatic forces between the separated charges, carrying momentum and energy back and forth faster than direct measurement can detect, while creating the macroscopic effects we experience as electromagnetic attraction. What makes these force-carrying photons different from the visible light streaming from your lamp or the radio waves broadcasting entertainment signals through the atmosphere? Virtual photons exist only during the brief intervals of their exchange between interacting charges, never propagating freely through space as independent particles that could be directly observed or measured, yet their effects accumulate to produce all the electromagnetic phenomena that characterize our physical world. Real photons, in contrast, represent genuine excitations of the electromagnetic field that can travel indefinitely through vacuum, carrying energy and information from their sources to whatever destinations they eventually encounter, whether those be retinas detecting visible illumination, antennas receiving communication signals, or solar panels converting radiant energy into electrical current. How remarkable that these same quantum entities serve dual roles as both force mediators maintaining the electromagnetic interactions that stabilize matter, and as independent energy carriers enabling radiation to transport power across cosmic distances. The fundamental nature of photons becomes apparent when we recognize that they cannot be decomposed into smaller constituents or explained as combinations of more basic particles, representing instead elementary excitations of the electromagnetic field itself that emerge whenever charged matter undergoes acceleration or energy transitions. What does it mean for something to be truly fundamental in physics? And how do we determine whether a particle represents a basic building block of nature or a composite structure made from simpler components? Modern particle accelerator. Experiments have revealed the internal structure of protons and neutrons, showing them to consist of quarks bound together by the strong nuclear force, while electrons appear to remain point-like and structureless even at the highest energies achievable with current technology. Photons likewise show no evidence of internal components or substructure, behaving as indivisible quanta of electromagnetic field energy that cannot be broken apart or analysed into constituent elements. This elementary character connects photons directly to the mathematical structure of quantum field theory, where they emerge as the natural excitations of the electromagnetic field that fills all of space and time according to the elegant equations formulated by Maxwell and later refined through quantum mechanical principles. Understanding photons therefore means understanding one of nature's basic building blocks, a fundamental aspect of physical reality that participates in virtually every process involving charged matter throughout the observable universe. Why do photons play such a central role in both the microscopic quantum world of atomic interactions and the macroscopic classical realm of electromagnetic technology and astronomical phenomena? The answer lies in recognizing that electromagnetic forces operate across all scales without diminishing strength, unlike nuclear forces that remain confined to subatomic distances, making photon-mediated interactions responsible for binding atoms into molecules, molecules into materials, and materials into the complex structures that constitute planets, stars, and living organisms. The electric currents flowing through your nervous system depend upon photon exchange between charged ions and electrons, while the magnetic fields generated by those currents involve photons carrying angular momentum and creating the electromagnetic signatures that enable medical imaging techniques to monitor brain activity without invasive procedures. What would happen to our universe if photons suddenly ceased to exist, eliminating the electromagnetic force that maintains atomic structure and enables chemical reactions to proceed? Without photon-mediated interactions, electrons would no longer be bound to nuclei, chemical bonds would dissolve, and all the complex matter that comprises stars, planets, and biological systems would collapse into a chaotic mixture of unbound charged particles unable to form stable structures or sustain organized processes. What physical property determines how much force you need to accelerate an object from rest to any given velocity? And why does this same quantity also measure the gravitational attraction between celestial bodies across astronomical distances? Our everyday understanding of mass often centers around the intuitive notion of how much matter or substance an object contains, yet this seemingly simple concept reveals layers of complexity when examined through the lens of modern physics and Einstein's revolutionary insights about energy, momentum, and space-time geometry. Consider the familiar experience of pushing a shopping cart through a supermarket compared to nudging a feather with your finger, where the dramatic difference in required effort reflects the fundamental property we call inertial mass, which quantifies an object's resistance to changes in its state of motion. What makes a fully loaded grocery cart so much more difficult to accelerate than an empty one? And how does this resistance to acceleration connect to the deeper physics governing matter, energy, and the structure of atoms themselves? Newton's perspective on mass emphasized its role as the proportionality constant relating applied force to resulting acceleration, establishing the foundational equation F equals ma that governs classical mechanics and engineering applications from automotive design to spacecraft trajectories. This inertial mass determines how much momentum an object carries when moving at any particular velocity, explaining why stopping a speeding truck requires enormous braking forces, while halting a rolling tennis ball needs only gentle pressure from your hand. How does this mechanical definition of mass relate to the gravitational mass that determines how strongly objects attract each other through the universal force of gravitation described by Newton's law of universal attraction? The remarkable equivalence between inertial and gravitational mass, verified experimentally with extraordinary precision, provided one of the crucial insights leading Einstein toward his general theory of relativity, and the recognition that gravity represents curvature in space-time rather than a conventional force acting between separated masses. Modern physics has refined our understanding of mass through Einstein's famous mass-energy equivalence, revealing that what we call rest mass actually represents the energy content of an object when measured in its own rest frame, divided by the square of light's velocity in vacuum. What does this modern definition tell us about the fundamental nature of matter that differs from our classical intuitions based on everyday experience with solid objects? The rest energy includes contributions from the masses of constituent particles, plus the binding energies that hold those particles together, explaining why a helium nucleus weighs slightly less than the sum of its separate protons and neutrons due to the energy released during nuclear fusion reactions. This mass-energy perspective illuminates phenomena ranging from chemical reactions that involve tiny mass changes corresponding to molecular binding energies, to nuclear processes where significant mass converts to kinetic energy according to Einstein's equation, powering both stellar, fusion and atomic weapons through the transformation of matter into radiant energy. How do we measure or determine the rest mass of fundamental particles like electrons, quarks, and neutrinos that cannot be isolated and placed on conventional scales? Particle physicists employ sophisticated techniques involving magnetic field deflection, time of flight measurements, and collision dynamics to infer particle masses from their behavior in controlled experimental environments, often expressing results in units of energy divided by c² rather than conventional mass units. The concept becomes even more subtle when dealing with composite objects like atoms and molecules, where the total rest mass includes not only the masses of individual constituents, but also the positive and negative contributions from various interaction energies between those constituents. Chemical bonds typically involve such small binding energies that their mass equivalents remain negligible for practical purposes, while nuclear binding energies become significant enough to affect atomic masses measurably, creating the mass defects that power stellar nucleosynthesis and enable nuclear technology applications. What happens to our understanding of mass when objects move at velocities approaching the speed of electromagnetic radiation, where relativistic effects become important? Einstein's special relativity reveals that the relationship between momentum and velocity becomes more complex at high speeds, leading to the concept of relativistic mass that increases with velocity, though modern physicists prefer to work with invariant rest mass and relativistic energy-momentum relationships that remain consistent across all reference frames. Understanding mass in its modern context provides essential background for comprehending why certain particles like photons can carry energy and momentum while possessing zero rest mass, a seemingly paradoxical combination that becomes comprehensible only through the complete energy-momentum relation E² equals P² C² plus m² C4 that governs all particles whether massive or massless. If this exploration of mass and its deeper meanings resonates with your curiosity about the fundamental nature of matter and energy, your thoughtful engagement through likes, subscriptions and comments helps create a community of minds seeking understanding together in the most peaceful way possible. What distinguishes the intrinsic mass that an object possesses as a fundamental property of its existence from the apparent mass that varies depending upon its velocity relative to different observers moving through spacetime? The concept of rest mass, also called invariant mass, represents the most basic measure of an object's matter content, determined when that object remains stationary relative to the measuring apparatus, providing a reference value that stays constant regardless of reference frame or observer motion. How do we define what it means for something to be truly at rest in a universe where Earth rotates, orbits the Sun, travels through our galaxy, and participates in cosmic expansion that carries entire clusters of galaxies through space at tremendous velocities? The answer requires recognizing that rest always remains relative to a chosen reference frame, so rest mass specifically denotes the mass measured by an observer who sees the object as motionless, regardless of how that object might appear to move from other perspectives. Consider a spacecraft traveling at half the speed of electromagnetic radiation relative to Earth, where terrestrial observers would measure its total relativistic energy as significantly greater than its rest energy, while astronauts aboard that vessel would measure their own rest mass using onboard instruments that register the same value the spacecraft possessed before launch. What physical mechanism causes objects to exhibit increased resistance to acceleration when moving at high velocities, requiring ever greater forces to achieve additional speed increments as velocities approach the cosmic speed limit? Einstein's special relativity reveals that this relativistic effect emerges from the fundamental structure of space-time itself, where energy and momentum transform between reference frames according to mathematical relationships that ensure physical laws remain consistent for all observers moving at constant velocities relative to each other. The relativistic mass concept, while historically important in early 20th century physics education, has largely fallen from favour among modern physicists who prefer working directly with invariant rest mass and total relativistic energy to avoid conceptual confusion about which mass value applies in different contexts. Why does the distinction between rest mass and relativistic mass become crucial for understanding high-energy particle physics, where accelerators routinely propel electrons, protons, and heavier nuclei to velocities exceeding 99% of light speed? At such extreme velocities, the total energy of accelerated particles can exceed their rest energy by a mere factors of thousands or millions, yet their invariant rest mass remains unchanged throughout the acceleration process, demonstrating that relativistic mass represents a measure of total energy rather than a fundamental alteration in the particle's intrinsic properties. This situation resembles how an object's apparent weight changes when you accelerate it upward in an elevator, where the sensation of increased heaviness reflects the dynamic forces involved, rather than any actual change in the object's gravitational mass or material composition. What happens to our measurements and calculations when we consistently use invariant rest mass instead of relativistic mass in our equations describing particle motion and energy transformations? The mathematical relationships become more elegant and physically transparent, with rest mass serving as a fundamental constant characterizing each type of particle, while relativistic energy and momentum vary smoothly with velocity according to precise transformation rules that preserve the structure of physical laws across all inertial reference frames. Photons present a particularly interesting case study in this distinction, possessing zero rest mass yet carrying definite amounts of relativistic energy and momentum that depend upon their frequency and direction of propagation. How can something with no rest mass nevertheless exhibit measurable effects through radiation pressure, gravitational deflection, and momentum transfer during absorption or scattering events? The resolution lies in recognizing that photons represent pure energy and momentum without any contribution from rest mass, traveling forever at light speed precisely because they lack the invariant mass that would constrain massive particles to subluminal velocities. Experimental verification of these relativistic effects spans nearly a century of increasingly precise measurements, from early observations of particle tracks in bubble chambers to modern particle accelerator experiments where relativistic calculations enable engineers to design magnetic focusing systems that guide charged particle beams around circular paths spanning kilometers of underground tunnels. What role does the rest mass versus relativistic mass distinction play in practical applications like nuclear medicine, where radioactive isotopes undergo decay processes that convert small amounts of rest mass into kinetic energy carried away by emitted particles? Medical imaging techniques such as positron emission tomography rely on precise calculations of rest mass differences between parent and daughter nuclei to predict the energies of annihilation photons produced when antimatter positrons encounter electrons in biological tissues, enabling physicians to reconstruct three-dimensional maps of metabolic activity within living organisms through purely non-invasive measurement procedures. If these profound connections between mass, energy, and the fundamental nature of reality spark something beautiful in your curious mind, your gentle subscription becomes part of a peaceful community where complex ideas unfold naturally, where wonder meets understanding, and where each person's journey toward knowledge enriches all our explorations together. How can we determine the rest mass of something that refuses to remain stationary even for the briefest instant, perpetually moving at the universe's fundamental speed limit without any possibility of slowing down or coming to a halt? The very definition of rest mass requires observing an object in its rest frame, where it appears motionless relative to the measuring apparatus, yet photons present an unprecedented challenge to this standard procedure because they maintain their cosmic velocity of approximately 300,000 kilometers per second, regardless of the observer's reference frame or motion. What does it mean to speak of rest energy for entities that exist only in states of constant motion, never achieving the stationary condition that would allow direct measurement of their intrinsic mass content? This conceptual puzzle reveals something profound about the nature of electromagnetic radiation that goes far beyond mere experimental inconvenience, pointing toward fundamental principles governing how energy, momentum, and mass relate to each other in the quantum mechanical description of physical reality. Consider how physicists typically measure particle masses by observing their behavior in magnetic fields, where charged particles follow curved trajectories with radii determined by their momentum to charge ratios, or by analysing collision dynamics where conservation laws allow inference of participant masses from measured energies and angles. What experimental strategies could possibly work for photons that cannot be deflected by magnetic fields due to their electrical neutrality and cannot be brought to rest for direct weighing on even the most sensitive balance? Traditional mass measurement techniques fail completely when applied to electromagnetic radiation, creating an apparently insurmountable barrier to determining whether photons possess any rest mass whatsoever. The problem deepens when we recognize that photons can be absorbed, transforming their energy into other forms such as kinetic motion of charged particles or thermal vibrations in absorbing materials. Yet during these interactions, the photon itself ceases to exist as an independent entity, making it impossible to measure its properties after bringing it to rest. How can we study the rest mass of something that vanishes whenever it stops moving, leaving only its energy and momentum to be redistributed among other particles and fields? This vanishing act suggests that photon existence depends essentially upon motion, that these electromagnetic quanta cannot survive without their characteristic velocity through spacetime. Laboratory attempts to slow down or trap photons using various techniques have succeeded only in converting them into other forms of energy or storing their effects in material systems, never achieving the goal of observing a stationary photon whose rest mass could be measured through conventional procedures. What happens when researchers try to confine electromagnetic radiation within perfect reflective cavities, bouncing photons back and forth between mirrors in attempts to create effectively stationary light? Even in such systems, individual photons continue travelling at light speed along their zigzag paths, never actually coming to rest despite being confined to limited spatial regions. The mathematical description of photon properties through quantum field theory provides theoretical guidance for this experimental dilemma, suggesting that photons might indeed possess exactly zero rest mass, rather than simply having rest masses too small to measure with current technology. Why would nature design fundamental particles with precisely zero rest mass? And what theoretical advantages emerge from this seemingly special case compared to particles with tiny but non-zero masses? The possibility of exactly massless photons connects to deep symmetries in electromagnetic theory, mathematical structures that require perfect masslessness to maintain their elegant self-consistency and predictive power across all scales, from quantum interactions to cosmic phenomena. Experimental searches for photon rest mass have pushed measurement sensitivity to extraordinary limits, placing upper bounds on possible photon mass values that remain trillions of times smaller than electron mass. Yet even these incredibly precise null results cannot definitively prove absolute zero mass, rather than merely confirming that any existing mass lies below detection thresholds. How do scientists interpret these increasingly stringent experimental limits? And what confidence can we place in theoretical predictions that photon rest mass equals exactly zero, rather than some unimaginably small positive value? The convergence of experimental evidence and theoretical requirements creates compelling arguments for true photon masslessness, suggesting that this apparent measurement problem actually reveals something fundamental about electromagnetic radiation and its role in the structure of physical law. This situation represents far more than mere technical difficulty in experimental physics, pointing instead toward profound insights about how massless particles must behave according to relativistic constraints and quantum field theoretical consistency requirements. What emerges from wrestling with the photon rest mass puzzle illuminates the deep connections between particle properties, spacetime geometry, and the mathematical symmetries that govern all electromagnetic interactions throughout our universe, revealing that some questions in physics have answers more beautiful and fundamental than the original problems might suggest. What makes a simple, algebraic expression containing just 4 symbols become the most recognizable equation in all of human knowledge, transcending scientific circles to achieve iconic status in popular culture while simultaneously revolutionizing our understanding of matter, energy, and the fundamental structure of reality itself? Einstein's equation E equals mc squared represents far more than mathematical elegance, revealing the profound truth that mass and energy constitute 2 manifestations of the same underlying physical quantity, interchangeable through processes that can transform matter directly into radiant power or convert pure energy back into material substance. How did this deceptively compact formula emerge from Einstein's contemplation of moving reference frames and the constancy of electromagnetic radiation velocity, leading to insights that would reshape physics, enable nuclear technology, and illuminate the energy sources powering stars across cosmic distances. The equation tells us that every gram of matter contains approximately 90 petajoules of energy, equivalent to the explosive power of 21 kilotons of TNT, or enough electricity to supply a typical household for several thousand years, demonstrating why the speed of light squared serves as such an enormous conversion factor between mass and energy units. What physical processes can actually achieve this complete transformation between matter and energy, releasing the tremendous power locked within atomic nuclei and subatomic particles? Nuclear fusion reactions occurring within stellar cores convert approximately 0.7% of hydrogen mass into energy, providing the radiant output that illuminates our solar system and sustains life on Earth through photosynthesis and climate regulation. While nuclear fission processes split heavy uranium or plutonium nuclei into lighter fragments, releasing binding energy that powers both electrical generation plants and devastating weapons. The mathematical beauty of mass energy equivalence extends beyond its practical applications to reveal something profound about the nature of physical law, suggesting that conservation principles governing isolated systems must account for both material content and energetic content as aspects of a single conserved quantity that can flow between different forms but never disappears entirely. How do particle accelerator experiments demonstrate this interchangeability by creating new particles from pure kinetic energy when high-speed projectiles collide with stationary targets? The conversion works both ways, with matter and antimatter annihilation producing gamma rays that carry away the total rest energy of the destroyed particles, while pair production processes can create electron-positron pairs from sufficiently energetic photons interacting near atomic nuclei. Chemical reactions also involve mass-energy transformations, though the binding energy changes remain so minute that conventional scales cannot detect the mass differences between reactants and products, requiring extraordinarily precise measurement techniques to verify that molecular bond formation releases energy corresponding to measurable decreases in total system mass. What role does this mass-energy relationship play in understanding why certain atomic nuclei remain stable, while others undergo radioactive decay, spontaneously transforming into lighter elements while releasing energy in forms ranging from alpha particles to gamma radiation? The equation predicts that nuclear configurations with lower total mass will be energetically favored, driving decay processes that reduce system mass while increasing kinetic energy of emitted particles and electromagnetic radiation. Stars demonstrate mass energy conversion on truly astronomical scales, consuming millions of tons of hydrogen every second, and converting approximately 4 million tons of that mass into pure energy that radiates outward as electromagnetic radiation, spanning the entire spectrum from radio waves to X-rays. How does this continuous mass-to-energy transformation enable our Sun to maintain its luminous output for billions of years without exhausting its nuclear fuel supply or collapsing under its own gravitational attraction? The fusion processes occurring at temperatures exceeding 10 million degrees Celsius overcome electromagnetic repulsion between positively charged hydrogen nuclei, allowing strong nuclear forces to bind them into helium while releasing binding energy that eventually reaches Earth as the gentle warmth and visible illumination supporting terrestrial ecosystems. Yet Einstein's famous equation represents only a special case of a more comprehensive relationship that governs all particles, whether massive or massless, at rest or in motion, providing the foundation for understanding why photons behave so differently from material objects despite carrying energy and momentum through their interactions with matter and fields. What additional insights emerge when we examine the complete energy-momentum relationship that reduces to E equals mc, squared only for objects at rest, while revealing more complex connections between particle energy, momentum, and mass for systems involving motion or massless entities like electromagnetic radiation? The fuller mathematical framework encompasses phenomena ranging from relativistic particle dynamics to cosmological expansion, from quantum field fluctuations to gravitational wave propagation, demonstrating how Einstein's initial insight into mass-energy equivalence opened pathways toward understanding the deepest principles governing space, time, matter, and energy throughout our universe. What elegant mathematical relationship governs all particles throughout the universe, whether they possess mass or remain massless, whether they move slowly through everyday experience or race at cosmic velocities approaching the fundamental speed limit of spacetime itself? The complete energy-momentum relation reveals itself through the equation E squared equals mc squared, quantity squared plus pc quantity squared, where E represents total energy, m denotes rest mass, P indicates momentum, and C symbolizes the velocity of electromagnetic radiation in vacuum. How does this comprehensive formula encompass both the familiar mass-energy equivalence that applies to stationary objects and the more complex dynamics governing particles moving at relativistic speeds where conventional mechanics breaks down? The mathematical structure resembles the Pythagorean theorem for right triangles, where two perpendicular components combine to determine the length of the hypotenuse. Except here, we have energy components rather than spatial dimensions combining according to the geometry of spacetime rather than ordinary Euclidean space. When momentum equals zero because an object remains at rest relative to the observer, the equation simplifies dramatically to yield E equals mc squared, the famous relationship that captures headlines and popular imagination while representing only one special case of the broader energy-momentum framework. What happens when we consider particles moving at significant fractions of light speed, where momentum contributions become comparable to, or even exceed the rest mass energy component? The total energy increases smoothly with velocity according to relativistic mechanics, asymptotically approaching infinity as particle speed approaches the cosmic limit, explaining why accelerating massive objects to light speed requires infinite energy input and therefore remains physically impossible. High-energy particle accelerators routinely demonstrate this relationship by propelling protons, electrons, and heavier nuclei to velocities exceeding their 9% of light speed, where the momentum contribution dominates over rest mass energy, and the total energy can exceed rest energy by factors of thousands or millions. How do engineers design magnetic focusing systems for these relativistic particle beams when classical mechanics predictions would place particle trajectories far from their actual paths? The complete energy-momentum relation provides the accurate framework for calculating particle behavior under these extreme conditions, enabling precise control over beam steering, collision timing, and energy deposition in experimental targets. The right triangle analogy helps visualize how these energy components combine, with rest mass energy forming one leg, momentum energy forming the perpendicular leg, and total energy representing the hypotenuse, whose length exceeds either individual component except in the limiting cases, where one component vanishes entirely. What physical meaning can we assign to this geometric relationship between energy quantities? And why does nature seem to organize fundamental relationships according to mathematical structures that appear in classical geometry? The answer connects to the underlying geometry of spacetime itself, where intervals between events remain invariant under coordinate transformations just as triangle side lengths remain constant under rotations in ordinary space. Photons provide the most striking example of this energy-momentum relationship in action, possessing zero rest mass, yet carrying definite amounts of energy and momentum, related through E equals pc, demonstrating how massless particles derive all their energy from motion rather than material content. Why do electromagnetic radiation quanta follow this simplified version of the general relationship? And what constraints does this place upon their possible behaviors and interactions? The zero rest mass condition forces photons to travel forever at light speed, unable to slow down, speed up, or achieve rest relative to any observer, making motions an essential aspect of their existence. Rather than merely something they happen to be doing, massive particles can exist at rest, and possess rest energy even without motion, while massless particles like photons can exist only while moving, and derive their energy entirely from momentum, creating a fundamental distinction between matter and radiation that pervades all physical phenomena. How does this energy-momentum relationship extend to composite systems containing multiple particles, where the total system energy includes kinetic energies of individual components plus interaction energies between them? A moving automobile consists of countless atoms and molecules, each contributing its own energy-momentum combination to the overall system behavior. Yet the macroscopic vehicle obeys the same mathematical relationship governing individual elementary particles. The complete equation also describes more exotic systems such as bound states of quarks, forming protons and neutrons, where strong nuclear forces create complex energy distributions that give rise to most of the visible matter mass in our universe, despite quarks themselves contributing only a small fraction of nucleon rest energy. What extraordinary transformation occurs when we substitute zero for the mass term in Einstein's complete energy-momentum relationship, revealing a profound constraint that governs the behavior of electromagnetic radiation throughout our universe? When rest mass equals zero, the equation E squared equals mc squared quantity squared plus pc, quantity squared reduces dramatically to E squared equals pc quantity squared, which simplifies further to yield the elegant relationship E equals pc that describes all massless particles including photons, gravitons and gluons under certain conditions. How does this mathematical simplification illuminate the fundamental difference between matter and radiation, between particles that can achieve rest and those condemned to eternal motion at the cosmic speed limit? The zero rest mass condition creates an inescapable connection between energy and momentum for these particles, where every joule of energy corresponds to a specific amount of momentum divided by the speed of light, eliminating the rest energy component that allows massive particles to possess energy even when stationary relative to an observer. This relationship explains why electromagnetic radiation exhibits such unique properties compared to material objects, deriving its entire energy content from motion rather than from intrinsic mass, making velocity an essential aspect of photon existence rather than merely a temporary state that could be altered through applied forces. What profound implications emerge from recognizing that photons cannot slow down because they possess no rest mass to provide energy in a stationary state? The mathematics reveals that massless particles must travel at exactly light speed in vacuum, never faster and never slower, because any other velocity would violate energy conservation or create mathematical inconsistencies in the fundamental equations governing electromagnetic phenomena. Consider how this constraint affects our understanding of light propagation through different media, where photons appear to slow down in glass, water, or other transparent materials, yet actually maintain their fundamental velocity between atomic interactions, with apparent deceleration resulting from absorption and re-emission processes that create delays rather than genuine speed changes. How do these seemingly minor interactions between electromagnetic radiation and atomic electrons accumulate to produce macroscopic effects like refraction, dispersion, and the beautiful rainbow patterns created when white light passes through prisms? Each individual photon continues traveling at light speed along its microscopic path, yet the collective behavior creates the illusion of reduced velocity as radiation navigates through the complex electromagnetic landscape created by bound electrons oscillating in response to incident waves. The energy-momentum relationship for massless particles also explains why photons can exert radiation pressure despite having no rest mass, transferring momentum to absorbing or reflecting surfaces through collisions that conserve both energy and momentum according to relativistic mechanics. What happens during these collisions between massless photons and massive particles? And how do conservation laws determine the resulting particle motions and energy distributions? When a photon strikes an electron, the interaction must conserve total energy and momentum while respecting the constraint that any surviving photon must continue traveling at light speed, leading to specific scattering angles and energy transfers that can be calculated precisely using the energy-momentum relationships for both massive and massless particles. Solar radiation pressure, though tiny compared to gravitational forces, becomes significant for spacecraft with large solar panels or reflective surfaces, requiring engineers to account for photon momentum transfer when designing orbital trajectories and attitude control systems for satellites operating in the intense electromagnetic environment near our star. How does the massless nature of photons enable them to escape from massive objects like stars and even black holes under certain conditions, carrying energy and information across cosmic distances that would trap any material particle? The absence of rest mass allows electromagnetic radiation to achieve escape velocity from gravitational fields that would prevent material objects from reaching freedom, though extremely strong gravitational fields can still bend photon paths and shift their frequencies through effects predicted by general relativity. High-energy gamma rays produced in stellar cores or nuclear reactions demonstrate the extreme energies that massless particles can carry, with individual photons possessing millions of times more energy than visible light quanta despite both types travelling, at identical velocities and obeying the same fundamental relationship between energy and momentum. What sets the upper limit on photon energy, and how do cosmic ray interactions create gamma rays with energies exceeding anything achievable in terrestrial laboratories? The answer lies in understanding that photon energy scales linearly with frequency according to Planck's relationship, allowing electromagnetic radiation to span an enormous range from low-frequency radio waves carrying minimal energy per quantum to ultra-high-frequency gamma rays that can trigger nuclear reactions and create particle-antiparticle pairs when interacting with matter or intense electric fields. The profound implication that photons with any rest mass could not travel at light speed revolutionizes our understanding of electromagnetic phenomena, revealing that masslessness represents not merely a convenient approximation, but an absolute requirement for maintaining the mathematical consistency of electromagnetic theory and the experimental observations that confirm light's universal velocity across all reference frames and cosmic distances. What invisible mathematical principles guide the fundamental forces of nature, ensuring that physical laws maintain their validity regardless of when we perform experiments, where we conduct observations, or how we orient our measuring apparatus in space? Symmetries represent profound organizing principles that constrain how the universe operates, revealing themselves through the remarkable fact that certain transformations leave physical systems completely unchanged, despite altering their mathematical descriptions or geometric configurations. Consider the elegant simplicity of a perfect circle, which appears identical after rotation through any angle about its center, demonstrating rotational symmetry that persists whether we turn it 1 degree or 180 degrees around its central axis. How does this geometric concept of invariance under transformation extend to the deepest levels of physics, where symmetries govern everything from the conservation of energy to the fundamental interactions between elementary particles? The mathematical beauty of symmetrical relationships in nature suggests something profound about the underlying structure of reality, as if the universe operates according to aesthetic principles that favour elegance, consistency, and mathematical harmony over arbitrary complexity or random variation. Physical laws themselves exhibit remarkable symmetries that ensure their validity across different reference frames, spatial locations, and temporal epochs, meaning that an experiment conducted in Tokyo yields identical results when repeated in London, assuming equivalent conditions and measurement procedures. What mechanism ensures this universal consistency of natural law? And why should physical principles remain constant across vast distances and time intervals spanning cosmic history? The answer lies in recognizing that space and time possess fundamental symmetries that prevent physical laws from depending arbitrarily on particular coordinates, locations, or orientations chosen by human observers for convenience in their calculations and measurements. Translation symmetry ensures that moving an entire experimental apparatus from one location to another does not affect the outcomes, while rotation symmetry guarantees that reorienting equipment in different directions leaves physical relationships unchanged, and time translation symmetry requires that identical experiments yield consistent results whether performed today or next century. How do these seemingly abstract mathematical concepts connect to concrete physical phenomena and the practical technologies that depend upon predictable natural behavior? The connection emerges through Noether's remarkable theorem, which establishes that every continuous symmetry corresponds to a conserved quantity that remains constant throughout physical processes regardless of the specific details of particle interactions or field dynamics. Energy conservation arises from time translation symmetry, ensuring that isolated systems maintain constant total energy because physical laws remain unchanged as time progresses from past through present toward future. Momentum conservation emerges from spatial translation symmetry, guaranteeing that isolated systems preserve their total momentum because physics operates identically at different locations throughout the universe. Angular momentum conservation follows from rotational symmetry, requiring that spinning systems maintain their rotational motion unless acted upon by external torques that break the symmetry of their environment. What happens when symmetries become broken, either spontaneously through phase transitions or explicitly through external influences that distinguish between previously equivalent states or directions, symmetry-breaking phenomena create some of the most fascinating effects in physics, from crystalline structures that select particular orientations despite the underlying rotational symmetry of atomic interactions to magnetic materials that develop preferred directions through spontaneous alignment of atomic magnetic moments below critical temperatures. The standard model of particle physics relies heavily on gauge symmetries, mathematical transformations that leave physical observables unchanged while altering the mathematical expressions used to describe electromagnetic weak nuclear and strong nuclear interactions. How do these abstract gauge transformations relate to concrete experimental observations, and why do physicists consider gauge symmetries essential for maintaining theoretical consistency across different mathematical formulations of the same physical theory? The gauge principle requires that all physically measurable quantities remain invariant under gauge transformations, ensuring that different mathematical descriptions of electromagnetic fields yield identical predictions for experimental outcomes, such as particle trajectories, interaction cross-sections, and energy transfer rates. Local gauge symmetries prove particularly powerful because they allow transformation parameters to vary independently at different spacetime points, creating much richer mathematical structures than global symmetries where transformation parameters remain constant throughout space and time. Why does this local character of gauge symmetries lead necessarily to the existence of force-carrying particles like photons, gluons, and intermediate vector bosons that mediate interactions between matter particles? The mathematical requirement for gauge invariance under local transformations introduces additional fields that become identified with the force carriers observed in high-energy physics experiments, connecting abstract symmetry principles directly to the particle spectrum that comprises our physical universe and determines the structure of atoms, nuclei, and all complex matter. What peculiar mathematical freedom allows physicists to describe identical electromagnetic phenomena using completely different sets of equations, yet always arrive at the same experimental predictions for measurable quantities like forces, energies, and particle trajectories? Electromagnetic theory possesses a remarkable gauge symmetry that permits multiple mathematical representations of the same physical situation, similar to how cartographers can create various map projections of Earth's surface using different coordinate systems while preserving essential geographical relationships between locations. How does this flexibility in mathematical description reflect something fundamental about the nature of electromagnetic fields, rather than merely representing arbitrary choices in computational convenience or algebraic manipulation? The key insight lies in recognizing that electromagnetic phenomena depend only upon field differences and relative quantities rather than absolute values, making certain mathematical transformations physically irrelevant even though they dramatically alter the appearance of the underlying equations. Consider how electrical circuits operate according to voltage differences between connected points rather than absolute voltage levels relative to some arbitrary reference, explaining why household electrical systems function identically, whether we define ground potential as 0 volts, negative 12 volts, or positive 47 volts. What happens when we extend this relative voltage concept to electromagnetic fields throughout space, allowing the electric potential to be redefined simultaneously at every point while preserving all physically observable effects? This transformation freedom constitutes the essence of gauge symmetry, where we can add any smooth function to the electric potential and subtract its time derivative from the vector potential without changing electric or magnetic field configurations that determine forces on charged particles and currents flowing through conducting materials. The mathematical formalism enables us to choose gauge conditions that simplify calculations for particular problems, much like selecting coordinate systems that exploit natural symmetries in geometric situations, yet the underlying physics remains completely independent of these convenient choices. How do electromagnetic waves propagate through vacuum according to Maxwell's equations, and why do these wave solutions maintain their essential character despite the gauge freedom that allows numerous mathematical descriptions of the same radiation pattern? The answer reveals that physically measurable quantities like energy density, momentum density, and radiation pressure depend only upon electric and magnetic field magnitudes and orientations, which remain invariant under gauge transformations even though the potentials from which these fields derive can be modified arbitrarily through suitable mathematical manipulations. Radio engineers exploit this gauge freedom when solving antenna radiation problems, choosing Coulomb gauge to simplify calculations in some situations while selecting Lorentz gauge for other applications that benefit from manifest relativistic covariance. Yet both approaches yield identical predictions for transmitted power, radiation patterns, and received signal strengths. What connects this abstract mathematical flexibility to concrete physical principles like charge conservation? And why does gauge symmetry play such a central role in modern quantum field theory formulations of electromagnetic interactions? Noether's theorem establishes a profound connection between gauge symmetry and electric charge conservation, demonstrating that the mathematical freedom to redefine electromagnetic potentials corresponds directly to the physical principle that electric charge can neither be created nor destroyed in isolated systems. This deep relationship means that gauge symmetry represents far more than computational convenience, embodying instead a fundamental aspect of how nature organizes electromagnetic phenomena to ensure consistency between field theory predictions and experimental observations of charge behavior in atomic, nuclear, and particle physics processes. Quantum electrodynamics extends classical gauge symmetry into the quantum realm, where gauge transformations act not only upon electromagnetic fields, but also upon the complex phases of charged particle wave functions, creating intricate mathematical structures that govern virtual photon exchange between interacting charges. How do these quantum gauge transformations maintain physical equivalence between different mathematical descriptions while introducing new phenomena like vacuum polarization and electromagnetic field fluctuations that have no classical analogues? The gauge principle requires that all observable remain independent of gauge choice, forcing the theory to include interaction terms between charged matter and electromagnetic fields that automatically ensure gauged invariance of scattering amplitudes, decay rates, and other experimentally measurable quantities. Local gauge symmetry proves especially powerful because transformation parameters can vary independently at different spacetime locations, creating mathematical constraints that lead inevitably to the existence of massless gauge bosons that mediate electromagnetic forces between separated charges. Why does this local character of electromagnetic gauge symmetry require photons to remain exactly massless? And how does this mathematical necessity connect to experimental observations of light propagation across cosmic distances? Any photon mass term in the electromagnetic Lagrangian would violate gauge invariance, destroying the mathematical consistency that ensures charge conservation and threatens the theoretical framework that successfully describes electromagnetic phenomena from atomic spectra to radio communications to stellar radiation processes. What catastrophic consequences would ripple through the fundamental structure of electromagnetic theory if photons possessed even the tiniest amount of rest mass? And why does this seemingly innocent modification threaten to collapse the entire mathematical framework that successfully describes everything from atomic structure to cosmic radiation? Adding mass terms to the electromagnetic field equations destroys the gauge symmetry that forms the bedrock of electromagnetic theory, creating mathematical inconsistencies that undermine the logical foundation upon which our understanding of electric and magnetic phenomena rests. How does this breakdown of gauge invariance cascade through the theoretical structure, violating conservation laws that experimental evidence supports with extraordinary precision across scales ranging from elementary particle interactions to galactic magnetic field configurations? The mathematical catastrophe begins when mass terms make the electromagnetic Lagrangian sensitive to arbitrary gauge choices that should leave all physical predictions unchanged, forcing previously equivalent mathematical descriptions to yield different experimental forecasts for identical physical situations. This violation of gauge invariance destroys the theoretical elegance that ensures electric charge conservation throughout all electromagnetic processes, from simple atomic transitions that emit single photons to complex plasma dynamics involving billions of interacting charged particles in stellar atmospheres. What experimental evidence supports the absolute necessity of charge conservation, and why would any violation of this principle create paradoxes that contradict countless observations accumulated over centuries of electromagnetic research? Laboratory experiments consistently demonstrate that electric charge remains perfectly conserved in nuclear reactions, particle accelerator collisions, and chemical processes where electrons transfer between atoms and molecules, establishing charge conservation as one of the most precisely verified principles in all of physics. The mathematical relationship between gauge symmetry and charge conservation, established through Noether's theorem, means that breaking gauge invariance necessarily implies charge non-conservation, creating theoretical predictions that flatly contradict experimental reality and forcing physicists to abandon either gauge, symmetry, or charge conservation as fundamental principles. Why does the structure of electromagnetic theory demand this particular symmetry rather than alternative mathematical formulations that might accommodate massive photons while preserving other desirable theoretical properties? The gauge principle ensures that physically meaningless mathematical artifacts cannot influence experimental predictions, requiring that observable quantities like forces, energies, and cross-sections remain independent of arbitrary choices in mathematical descriptions such as coordinate systems, origin locations, or potential function definitions. Massive photons would introduce additional mathematical degrees of freedom that couple to these arbitrary choices, making physical predictions depend upon unobservable gauge parameters and destroying the clear separation between mathematical convenience and physical reality that characterizes successful theoretical frameworks. The mathematical structure of quantum electrodynamics relies crucially upon massless photon exchange to maintain gauge invariance in quantum field theoretical calculations, where virtual photon propagators must exhibit specific mathematical forms that become impossible if photons possess any rest mass whatsoever. How do these mathematical requirements translate into concrete physical constraints on electromagnetic behavior, and what experimental signatures would reveal violations of photon masslessness if such violations actually occurred in nature? Massive photons would cause electromagnetic forces to exhibit finite range rather than extending indefinitely across cosmic distances, making Coulomb's law applicable only within limited spatial regions, beyond which electric fields would decay exponentially towards zero regardless of source charge magnitudes. Astronomical observations of planetary magnetic fields, interplanetary plasma dynamics, and galactic electromagnetic structures provide sensitive tests for possible photon mass effects, consistently confirming that electromagnetic forces maintain their strength across enormous distances without the exponential attenuation that massive photon exchange would inevitably produce. The mathematical elegance of massless electromagnetism extends beyond gauge symmetry to encompass the beautiful geometric structure of electromagnetic field equations, which exhibit conformal invariance, and other symmetries that disappear when mass terms break the delicate mathematical balance underlying Maxwell's equations. What aesthetic principles guide theoretical physicists in their preference for mathematically elegant formulations, and how do these aesthetic considerations relate to experimental success in describing natural phenomena? The history of physics reveals repeatedly that mathematical beauty often signals theoretical truth, with elegant equations typically providing more accurate descriptions of experimental data than ad hoc modifications designed to accommodate specific observations while sacrificing overall theoretical coherence. The universe's fundamental structure appears to favor mathematical relationships that exhibit symmetry, simplicity, and internal consistency, suggesting that photon masslessness represents not merely a convenient approximation, but an absolute requirement imposed by the deeper mathematical harmony underlying electromagnetic phenomena. The elegant mathematical structure requires photons to remain exactly massless to preserve the gauge symmetries that ensure theoretical consistency, experimental accuracy, and conceptual clarity in our understanding of how electromagnetic forces shape atomic structure, molecular chemistry, and the large-scale organization of matter throughout the cosmos. What ingenious experimental strategies have physicists devised to search for evidence of photon mass, pushing measurement sensitivity to limits so extraordinary that they probe whether electromagnetic radiation possesses even the most infinitesimal trace of rest mass imaginable. For nearly a century, researchers have pursued increasingly sophisticated approaches to detect any deviation from perfect masslessness in electromagnetic radiation, driven by the profound theoretical implications that even tiny photon masses would have for our understanding of fundamental physics and cosmology. How do scientists measure something so elusive that its upper bound currently stands at approximately 10 to the negative 54th power kilograms, a value so incredibly small that it represents less than 1/billionth of 1/billionth of 1/billionth of 1/billionth of 1/billionth of an electron mass, the experimental challenge requires detecting effects so subtle that they manifest only across astronomical distances or through precision measurements that strain the limits of current technology, yet the potential discovery of non-zero photon mass would revolutionize electromagnetic theory and force fundamental revisions to our understanding of gauge symmetry, charge conservation, and the mathematical structure underlying electromagnetism. One of the most sensitive experimental approaches involves studying planetary magnetic fields using spacecraft magnetometers that measure field strengths at various distances from magnetic sources, searching for deviations from the inverse square law behavior that massless electromagnetic theory predicts for static magnetic configurations. What observable signatures would massive photons create in these planetary magnetic field measurements? And why do such astronomical observations provide more sensitive tests than laboratory experiments conducted on Earth? Massive photons would cause electromagnetic forces to weaken more rapidly than expected with increasing distance, introducing exponential decay factors into Coulomb's law and magnetic field equations that would become detectable across the enormous spatial scales accessible through interplanetary spacecraft missions. The Pioneer and Voyager missions provided early opportunities to test electromagnetic field behavior across solar system distances, while more recent spacecraft including Cassini, Juno, and various Mars orbiters have collected magnetic field data with unprecedented precision throughout their extended operational lifetimes orbiting distant planets. Galactic magnetic fields offer even more sensitive testing, grounds for photon mass searches since these vast electromagnetic structures span thousands of light years and would exhibit clear signatures of massive photon effects if such effects existed at detectable levels. How do astronomers measure magnetic field strengths in distant galaxies, and what observational techniques enable them to map electromagnetic field configurations across cosmic distances that dwarf our solar system dimensions? Radio telescopes detect polarized emission from cosmic ray electrons spiraling through galactic magnetic fields, revealing field directions and approximate strengths through careful analysis of polarization patterns across different radio frequencies and spatial regions within galaxy images. The consistency of these galactic electromagnetic observations with massless photon theory places stringent constraints on possible photon mass values, ruling out masses larger than about 10 to the negative 18th power electron volts through the absence of observable field truncation or exponential decay across galactic dimensions. Laboratory experiments have also contributed to photon mass searches through precision tests of Coulomb's law at various distance scales, using sensitive electrometers and charged sphere configurations to detect any deviations from perfect inverse square force relationships. What experimental challenges arise when attempting to measure electromagnetic forces with sufficient precision to detect photon mass effects? And how do researchers account for systematic errors that could mimic the signals they seek? Environmental electromagnetic interference, thermal fluctuations, mechanical vibrations, and residual charge leakage create experimental backgrounds that often exceed the tiny signals expected from massive photon effects, requiring elaborate shielding, temperature control, and statistical analysis techniques to achieve meaningful sensitivity limits. Geophysical studies of Earth's magnetic field provide additional constraints through satellite measurements of magnetospheric structure and long-term monitoring of magnetic field variations that would reveal massive photon signatures if they existed above current detection thresholds. The cumulative effect of decades of increasingly sensitive measurements has established upper bounds on photon mass that will remain consistent with exact zero, supporting theoretical predictions while demonstrating the remarkable precision achievable through careful experimental design and patient data accumulation. Why do physicists continue pursuing ever more sensitive photon mass measurements despite the strong theoretical arguments for exact masslessness? And what discoveries might emerge if future experiments detected non-zero photon mass above current sensitivity limits? Even tiny violations of photon masslessness would signal new physics beyond the standard model, potentially revealing connections to dark energy, extra dimensions, or other exotic phenomena that could reshape our understanding of fundamental forces and cosmological evolution throughout the observable universe. What radical transformations would reshape our technological civilization and the fundamental structure of the universe if photons possessed even microscopic amounts of rest mass, forcing electromagnetic forces to operate according to completely different principles than those governing our current reality. The electromagnetic force would develop a finite range characterized by an exponential decay length inversely proportional to photon mass, similar to how the weak nuclear force remains confined to subatomic distances because its carrier particles possess substantial rest masses. How would this range limitation affect the planetary-scale electromagnetic phenomena that currently enable global communications, navigation systems, and the vast interconnected networks that define modern technological society? Radio signals propagating through Earth's atmosphere and space would experience frequency-dependent attenuation that increases with distance, making long-range communication increasingly difficult at higher frequencies while potentially rendering satellite links impossible beyond certain orbital altitudes depending upon the specific value of photon mass. The global positioning system relies critically upon precise timing relationships between atomic clocks aboard multiple satellites and ground-based receivers, yet massive photons would introduce frequency-dependent propagation delays that could accumulate into positioning errors measured in kilometers rather than the meter-scale accuracy that current GPS technology provides. What happens to the fundamental assumption underlying electromagnetic wave propagation when different frequencies travel at slightly different velocities through vacuum, violating the principle that all electromagnetic radiation maintains identical speed regardless of wavelength or energy content? This dispersion effect would cause broadband radio pulses to stretch and distort during transmission across cosmic distances, with higher frequency components arriving at receivers earlier or later than lower frequency parts depending upon the sign and magnitude of the mass-induced velocity differences. Astronomical observations would reveal this frequency-dependent propagation through timing measurements of pulsed radio sources like pulsars, whose extremely regular emission patterns provide natural clocks accurate enough to detect even tiny variations in electromagnetic wave speeds across the vast distances separating these stellar remnants from Earth. The modification of Coulomb's law at large distances would fundamentally alter atomic structure and chemical bonding, though these effects might remain undetectable for everyday matter if photon mass stayed below certain threshold values determined by typical atomic dimensions and binding energies. How would the exponential screening of electromagnetic forces affect the behavior of plasmas, the fourth state of matter that comprises most of the visible universe, including stellar interiors, solar wind, and the ionized gas filling intergalactic space? Plasma physics relies heavily upon long-range electromagnetic interactions between charged particles separated by distances much larger than atomic scales, yet massive photon effects would truncate these interactions beyond characteristic screening lengths, potentially destabilizing plasma configurations and altering the dynamics of stellar formation, solar activity, and cosmic ray propagation through galactic magnetic fields. Technological systems depending upon electromagnetic induction would operate differently in a universe with massive photons, since the coupling between changing magnetic fields and induced electric fields would weaken exponentially with distance according to the modified field equations that accommodate finite photon mass. What consequences would this have for electric power generation, transmission, and distribution systems that rely upon electromagnetic induction to transfer energy across substantial distances through transformer networks and transmission lines spanning continents? Motor and generator designs would require modification to maintain efficiency as electromagnetic field configurations developed range limitations that confined magnetic flux to smaller regions around current carrying conductors, potentially necessitating higher current densities or alternative technologies for mechanical energy conversion. Fiber optic communications would face fundamental limits imposed by frequency-dependent propagation velocities that could cause signal distortion and timing errors in high-speed digital networks, while wireless communication protocols might need redesign to accommodate the altered electromagnetic wave behavior across different frequency bands. How would spacecraft navigation and deep space communications adapt to an electromagnetic environment where signal strength decreases more rapidly with distance than current inverse square law predictions, potentially making interplanetary missions more challenging, or requiring more powerful transmitters and larger receiving antennas? The cosmic microwave background radiation that provides crucial evidence for Big Bang cosmology would exhibit different properties if photons possessed mass during the early universe, potentially altering temperature fluctuations, polarization patterns, and spectral characteristics that astronomers use to infer fundamental cosmological parameters like the density, and composition of dark matter and dark energy. Even biological systems might function differently in a universe with massive photons, since many physiological processes depend upon electromagnetic interactions operating effectively across cellular and molecular dimensions, from nerve impulse propagation to photosynthesis to the electromagnetic forces that maintain protein structures and enable enzymatic catalysis essential for life. What cosmic architecture depends absolutely upon the massless nature of electromagnetic radiation, enabling the vast interconnected web of forces that binds atoms into molecules, molecules into complex structures, and ultimately creates the rich tapestry of organization spanning from quantum scales to galactic clusters throughout our observable universe? The infinite range of electromagnetic interactions made possible by massless photons provides the fundamental scaffolding upon which all atomic structure depends, allowing electrons to orbit nuclei at precisely defined energy levels while maintaining the delicate balance between attractive electric forces and quantum mechanical motion that stabilizes every element in the periodic table. How does this electromagnetic foundation enable the intricate dance of chemical bonding that creates everything from simple water molecules to complex organic polymers, DNA, strands, and the sophisticated protein machinery operating within living cells? Without massless photons mediating electromagnetic forces across molecular dimensions, the electron sharing and charge distributions that characterize covalent bonds would decay exponentially with distance, preventing the formation of large molecules essential for biological processes and technological materials that define our modern world. The cosmic significance of photon masslessness becomes apparent when we consider how electromagnetic radiation carries information across unprecedented distances, enabling astronomers to study galactic structures formed billions of years ago, while providing direct observational evidence for cosmic evolution, stellar nucleosynthesis, and the large-scale distribution of matter throughout space. What remarkable properties allow ancient photons emitted by distant quasars and early galaxies to traverse billions of light-years without losing their essential characteristics, arriving at Earth's telescopes with spectral signatures intact despite their incredibly long journeys through expanding space-time? The massless nature ensures that these electromagnetic messengers maintain their fundamental speed and frequency relationships throughout cosmic transit, suffering only the redshift effects predicted by general relativity rather than the exponential attenuation or frequency-dependent delays that massive photons would introduce across such enormous distances. Stellar formation and evolution depend critically upon electromagnetic processes operating efficiently across the vast scales characteristic of stellar interiors, where radiation pressure from countless photon interactions helps maintain hydrostatic equilibrium against gravitational collapse, while enabling energy transport from nuclear fusion cores to stellar surfaces, where electromagnetic radiation finally escapes into interstellar space. How do the electromagnetic forces mediated by massless photons enable the complex feedback mechanisms that regulate stellar burning rates, determine stellar lifetimes, and control the nucleosynthesis processes that forge heavy elements from primordial hydrogen and helium? The infinite-range electromagnetic interactions allow charged particles throughout stellar plasma to communicate instantaneously through virtual photon exchange, creating the collective electromagnetic behavior necessary for plasma stability, magnetic field generation, and the sophisticated magneto-hydrodynamic phenomena that shape stellar atmospheres and drive solar wind interactions with planetary magnetospheres. Galactic magnetic fields spanning thousands of light-years provide another spectacular demonstration of electromagnetic forces operating across cosmic scales, organizing interstellar plasma flows, influencing cosmic ray propagation, and participating in the complex dynamical processes that govern galactic structure formation and evolution over cosmological timescales. What role do these vast electromagnetic configurations play in regulating star formation rates, channeling interstellar gas flows, and maintaining the delicate balance between gravitational attraction and electromagnetic pressure that determines galactic morphology and stability? The massless photons that mediate these enormous magnetic structures enable electromagnetic effects to persist without decay across the millions of years required for galactic rotation, stellar orbit completion, and the slow evolutionary processes that transform spiral galaxies through interactions with neighboring systems and intergalactic environments. The rich complexity we observe throughout the universe emerges directly from the infinite-range electromagnetic interactions that massless photons provide, enabling atoms to form complex molecules, molecules to assemble into intricate biological systems, and electromagnetic radiation to carry energy and information across cosmic distances that connect all scales of physical organization from quantum mechanics to cosmology. Without massless electromagnetic mediators, atomic structure would collapse beyond microscopic distances, chemical reactions would become impossible except at contact separations, and the electromagnetic radiation that illuminates our universe would decay rapidly with distance, rather than propagating freely across billions of light years to reveal the cosmic history written in starlight. How does the elegant mathematical requirement for exact photon masslessness connect directly to the practical reality of every electromagnetic phenomenon we experience, from the neural electrical activity enabling conscious thought to the electromagnetic spectrum observations that reveal exoplanets orbiting distant stars? The masslessness of light enables not only the fundamental forces holding matter together, but also the observational capabilities that allow conscious beings to study and appreciate the magnificent complexity emerging from these simple yet profound physical principles governing electromagnetic interactions throughout our cosmos. What profound truth emerges when we realize that for electromagnetic radiation, the concepts of existence and motion represent not separate characteristics but two aspects of a single, indivisible reality that defines the essential nature of photons throughout our universe? Unlike material particles that can transition between states of rest and movement, photons embody pure motion as their fundamental mode of being, forever locked into their cosmic velocity, not through external constraints, but because motion itself constitutes their very essence. How does this inseparable connection between photonic existence and perpetual movement challenge our everyday intuitions about objects that can start, stop, accelerate, and decelerate according to applied forces and changing circumstances? The electromagnetic quanta streaming from your reading lamp racing across interstellar distances from distant stars and carrying radio signals between communication towers all participate in this eternal dance at exactly the same speed, unable to deviate from their prescribed velocity even when interacting with massive gravitational fields, dense plasma environments, or complex electromagnetic configurations. What makes this universal speed constraint so absolute that no known force or interaction can cause photons to travel faster or slower than the fundamental constant that characterizes electromagnetic propagation through vacuum? The answer lies in recognizing that photons represent excitations of the electromagnetic field itself, rather than discrete objects moving through space, making their velocity an intrinsic property of spacetime geometry rather than a circumstantial characteristic that might vary under different conditions. Every photon that emerged during the cosmic microwave background radiation approximately 380,000 years after the Big Bang has maintained this identical velocity throughout its subsequent journey across expanding space, cooling through cosmological redshift yet never changing its fundamental speed despite traversing billions of light years of evolving universe filled with galaxies, dark matter, and mysterious dark energy. How remarkable that these ancient electromagnetic messengers continue their eternal journey at precisely the same rate as photons created moments ago in fluorescent bulbs, laser diodes, or stellar fusion reactions occurring throughout our galaxy and beyond. The constancy reveals something beautiful about the mathematical structure underlying physical reality, where certain relationships remain invariant despite the passage of cosmic time and the dramatic evolution of matter and energy configurations throughout the observable universe. Photons cannot slow down because deceleration would require them to possess rest mass that could provide energy in a stationary state, yet they're massless. Nature eliminates this possibility and forces them to derive all their energy from motion, according to the fundamental relationship E=pc that governs massless particle dynamics. They cannot speed up because the velocity of electromagnetic propagation represents the maximum rate at which any causal influence can travel through spacetime according to special relativity, making light speed not merely a characteristic of electromagnetic phenomena, but the universal limit governing all physical interactions and information transfer processes. What about changing direction, the one degree of freedom that photons retain while maintaining their prescribed speed through interactions with matter, fields, and curved spacetime geometries? Reflection, refraction, scattering, and gravitational lensing all demonstrate how electromagnetic radiation can alter its propagation direction while preserving its fundamental velocity, creating the rich variety of optical phenomena that enable vision, photography, telecommunications, and astronomical observations of cosmic structures across unprecedented distances. The necessity of motion for photonic existence creates a beautiful symmetry in nature, where massless particles embody pure kinetic energy, while massive particles can possess both kinetic and rest energy, depending upon their reference frame and velocity relative to observers. This complementary relationship between matter and radiation reflects deeper principles about how energy manifests in different forms throughout physical systems, from the binding energies that hold atomic nuclei together to the electromagnetic radiation that carries surplus energy away from nuclear reactions and stellar processes. Motion for electromagnetic radiation represents not something photons happen to be doing temporarily, but rather something they fundamentally are throughout their entire existence, from creation through propagation to eventual absorption or interaction with matter that converts their energy into other forms while ending their independent existence as free electromagnetic quanta. How does this essential nature of photonic motion connect to broader themes about the relationship between form and function in physics, where mathematical structures often dictate physical properties and behaviors that might seem arbitrary from everyday experience? The inseparability of existence and motion for photons exemplifies how fundamental particles derive their characteristics not from external influences, but from the intrinsic mathematical relationships that define their roles within the broader framework of quantum field theory and relativistic spacetime geometry that governs all electromagnetic phenomena, from quantum scales to cosmological distances. What remarkable convergence occurs when three of the most powerful theoretical frameworks in physics arrive at identical conclusions about photon behavior through completely independent lines of reasoning, suggesting that massless electromagnetic radiation represents a fundamental organizing principle woven into the very fabric of reality. Special relativity approaches the question through spacetime geometry and the universal speed limit, revealing that particles with zero rest mass must travel at the cosmic velocity constant to satisfy the energy and momentum relationships that govern all matter and radiation throughout the universe. Quantum mechanics tackles the same problem from the perspective of wave-particle duality and energy quantization, demonstrating how electromagnetic field oscillations create discrete energy packets that carry momentum despite lacking rest mass, according to the fundamental relationship connecting frequency, wavelength, and propagation velocity through Planck's constant. Gauge theory examines photon masslessness through the lens of mathematical symmetry and field invariance, proving that electromagnetic interactions require exactly massless mediators to preserve charge, conservation and maintain theoretical consistency across all reference frames and interaction scenarios. How does this threefold confirmation from distinct theoretical approaches strengthen our confidence in conclusions about photonic nature while revealing something profound about the interconnectedness of physical principles operating at different scales and energy regimes? The mathematical elegance emerges most clearly when we recognize that each theoretical framework could have predicted different behaviors for electromagnetic radiation. Yet all three converge upon identical requirements for zero rest mass and constant velocity propagation that creates a unified understanding spanning classical electromagnetism, quantum field theory, and relativistic spacetime physics. Special relativity contributes the insight that massless particles must achieve the universal speed limit to satisfy energy conservation and maintain consistent causal relationships across all inertial reference frames, while quantum mechanics adds the recognition that electromagnetic field energy arrives in discrete packets whose individual properties follow precise mathematical rules connecting particle and wave characteristics through fundamental constants of nature. Gauge theory provides the deepest explanation by demonstrating that photon masslessness emerges necessarily from the symmetry requirements that ensure electromagnetic theory remains mathematically consistent and physically meaningful across all possible experimental configurations and observational circumstances. What aesthetic principles guide physicists in recognizing when theoretical convergence signals fundamental truth rather than mere coincidence? And how do mathematical beauty and experimental verification work together to establish confidence in our understanding of natural phenomena? The history of physics reveals repeatedly that the most elegant mathematical formulations often describe physical reality most accurately, suggesting that nature operates according to principles that favor simplicity, symmetry, and mathematical harmony over arbitrary complexity or random relationships between different aspects of the same underlying phenomena. The beautiful mathematics describing massless particle dynamics exhibits internal consistency that extends far beyond electromagnetic radiation to encompass all gauge theories in the Standard Model, where strong nuclear forces mediated by massless gluons and electroweak interactions involving massless photons all follow similar mathematical patterns despite operating at vastly different energy scales and distance ranges. How do these abstract mathematical symmetries manifest as concrete physical effects that we can observe, measure, and utilize in technological applications ranging from quantum computers to medical imaging systems to global communication networks? The connection between mathematical abstraction and physical reality becomes apparent through experimental tests that consistently confirm theoretical predictions derived from symmetry principles, gauge invariance requirements, and relativistic constraints that initially appeared to represent pure mathematical speculation rather than descriptions of measurable natural phenomena. Electromagnetic radiation demonstrates this connection most vividly through its universal properties that remain constant across all electromagnetic frequencies, from radio waves with wavelengths measured in kilometers to gamma rays with wavelengths smaller than atomic nuclei, yet all traveling at identical velocity and exhibiting identical relationships between energy, frequency, and momentum. The universe reveals its deepest truths through elegant principles that unify apparently disparate phenomena under common mathematical frameworks, showing how electromagnetic interactions, weak nuclear decays, and strong nuclear binding all emerge from similar gauge theoretical structures that require massless mediators to maintain their essential symmetries and conservation laws. What makes this mathematical unity so compelling is not merely its aesthetic appeal, but its practical power in predicting new phenomena, explaining previously mysterious observations, and enabling technological developments that depend upon precise understanding of fundamental physical relationships governing matter, energy, and their interactions across all scales from quantum mechanics to cosmology. The convergence of special relativity, quantum mechanics, and gauge theory around photon masslessness exemplifies how the universe seems to operate according to mathematical principles that exhibit remarkable internal consistency, suggesting that physical reality itself may be fundamentally mathematical in nature, rather than simply being describable through mathematical tools and techniques developed by human minds seeking patterns in natural phenomena. What new perspective emerges when you look around your immediate environment and recognize that every glimmer of illumination, every subtle reflection, and every gentle glow represents countless individual messengers that have never experienced a single moment of rest throughout their entire existence? The warm radiance from your reading lamp consists of photons born mere nanoseconds ago in the tungsten filament, yet these fresh electromagnetic quanta already participate in the same eternal dance that has characterized light since the first moments after cosmic creation, joining an unbroken stream of motion that connects your present experience to the deepest history of our universe. How does this realization transform your perception of something as ordinary as the brightness filling your room, revealing it as a manifestation of fundamental physical principles that operate identically, whether we examine household electronics or the most distant astronomical phenomena observable through our most powerful telescopes? Every photon, illuminating these words, emerge from its source already traveling at the cosmic speed limit, having instantaneously achieved the velocity that it will maintain throughout its journey from lamp to page to your retina, where its energy finally converts into the neural electrical signals that enable reading comprehension and conscious awareness. The screen glow from electronic devices surrounding you carries electromagnetic radiation that shares essential characteristics with the cosmic microwave background, that faint afterglow from the Big Bang still detectable throughout space as evidence of our universe's origin approximately 13.8 billion years ago. What profound connection links the modern photons streaming from LED displays to those ancient electromagnetic messengers that began their journey when the universe first became transparent to radiation, cooling sufficiently for neutral atoms to form and allowing light to propagate freely across expanding spacetime? Both ancient cosmic radiation and contemporary electronic emissions travel at identical velocity, obey identical energy-momentum relationships, and exhibit identical massless particle behavior despite originating under vastly different circumstances separated by cosmic ages and involving completely different physical processes and energy scales. The morning sunlight that will stream through your windows tomorrow carries electromagnetic energy generated through nuclear fusion reactions in the solar core, where hydrogen nuclei combine to form helium while releasing binding energy that eventually reaches Earth as the life-sustaining radiation that powers photosynthesis, drives weather patterns, and maintains the thermal equilibrium that enables complex chemistry and biological processes throughout terrestrial ecosystems. How remarkable that these solar photons completed their 8-minute journey across interplanetary space at precisely the same speed as artificial illumination from incandescent bulbs, fluorescent tubes, and semiconductor light sources, demonstrating the universal character of electromagnetic propagation regardless of source mechanisms or energy origins. Even the faint starlight visible on clear evenings represents electromagnetic radiation that maintained its fundamental velocity throughout journeys lasting years, decades, centuries, or millennia. Depending upon stellar distances, arriving at your location with spectral signatures intact despite travelling through interstellar space filled with gas, dust, magnetic fields, and gravitational influences that could deflect, scatter, or absorb electromagnetic energy while leaving its essential speed unchanged. We live constantly surrounded by particles that embody pure motion, electromagnetic quanta that exist only while travelling and cease to exist whenever they transfer their energy to matter through absorption, reflection, or scattering processes that end their independent propagation while converting their kinetic energy into thermal motion, chemical reactions, or electrical signals within detecting systems. What does it mean to share our environment with entities whose very existence depends upon perpetual movement at the universe's fundamental speed limit, never slowing down despite interactions with countless obstacles and never speeding up regardless of how much additional energy they might encounter during their journeys? The photons reaching you from every direction carry stories written in electromagnetic language about their origins. Whether those sources involve stellar nuclear reactions, atmospheric lightning discharges, electronic device operations, or thermal radiation from objects warmed by absorbed sunlight and re-emitting that energy as infrared electromagnetic waves invisible to human vision but detectable through specialized sensors. This understanding of light's eternal journey need not overwhelm or complicate your appreciation of familiar illumination, but rather can settle as gently as evening light itself, adding depth and wonder to everyday visual experiences while connecting your immediate surroundings to the vast cosmic processes that generate, propagate, and sustain electromagnetic radiation throughout our universe, from quantum scales to galactic dimensions. The next time you flip a switch or step into sunlight, remember that you are witnessing the continuation of motion that began with electromagnetic field fluctuations in the quantum vacuum, and will persist until these photons eventually encounter matter that absorbs their energy, ending their independent existence while contributing to the ongoing dance between radiation and matter that characterizes all electromagnetic phenomena throughout space and time. What threads of understanding have we woven together during this gentle exploration, connecting the simple act of illumination in your immediate surroundings to the profound mathematical principles that govern electromagnetic phenomena across all scales from atomic interactions to cosmic evolution? Our journey began with familiar observations about the instant response of electric lights and the unchanging speed of electromagnetic radiation, yet gradually revealed how these everyday experiences reflect fundamental aspects of reality that Einstein, Maxwell, and countless other physicists have spent centuries investigating through experimental research and theoretical contemplation. How does recognizing the massless nature of photons and their eternal motion at light speed enhance, rather than diminish, the wonder we feel when witnessing natural phenomena like sunrise rainbow formation, or the gentle glow of bioluminescent organisms that evolved to create their own electromagnetic radiation? The interconnectedness of physical laws reveals itself most beautifully through the way special relativity, quantum mechanics, and gauge theory all converge upon identical conclusions about photon behavior, suggesting that our universe operates according to mathematical principles so fundamental that they manifest consistently across different theoretical approaches and experimental methodologies. The conservation laws, symmetry principles, and energy and momentum relationships that require photons to remain massless and travel at the cosmic speed limit also govern nuclear reactions in stellar cores, chemical bonding in complex molecules, and the electromagnetic forces that enable neural activity within the biological systems contemplating these very concepts. What emerges from this synthesis is not merely technical knowledge about electromagnetic radiation, but a deeper appreciation for how mathematical elegance and experimental observation work together to reveal the underlying structure of physical reality, where abstract theoretical principles translate directly into concrete phenomena that we can observe, measure, and incorporate into technological applications that define modern civilization. The gauge symmetries that forbid photon mass also ensure charge conservation throughout all electromagnetic interactions, while the relativistic constraints that lock electromagnetic radiation into its cosmic velocity simultaneously guarantee that information and causal influences cannot propagate faster than light speed, maintaining the logical consistency of cause and effect relationships across space and time. How does understanding these connections between seemingly disparate aspects of physics encourage continued curiosity about natural phenomena rather than providing final answers that might diminish the sense of mystery and wonder that motivates scientific investigation? The beauty of physical law lies not in eliminating mystery, but in revealing deeper questions and more subtle relationships that connect familiar experiences to cosmic processes operating across scales that stretch human imagination. From quantum fluctuations in electromagnetic fields to the propagation of gravitational waves across billions of light-years of expanding space-time, the mathematical frameworks that describe photon masslessness also apply to other fundamental particles and interactions throughout the standard model of particle physics, suggesting that our exploration of electromagnetic radiation provides insights into broader themes about how nature organizes matter, energy, and the forces that govern their interactions at the most fundamental level currently accessible to experimental investigation. Thank you for joining this peaceful expedition through ideas that span from household illumination to cosmic radiation, allowing complex concepts to unfold naturally without pressure or urgency while maintaining the wonder that makes scientific exploration such a rewarding intellectual adventure. The quiet appreciation for mathematical elegance and physical beauty that emerges from understanding why photons cannot stop moving reflects something profound about how human consciousness can grasp abstract principles that govern natural phenomena, connecting our everyday experience of electromagnetic radiation to universal laws that operate throughout space and time. Rather than reaching dramatic conclusions that claim to have solved all mysteries about light and electromagnetic radiation, our exploration reveals how each answer opens pathways toward new questions about quantum field theory, cosmological evolution, and the relationship between mathematical structure and physical reality that continues to challenge and inspire researchers across many scientific disciplines. The gentle settling of understanding resembles how evening light gradually transitions into darkness, not through abrupt changes, but through smooth variations that allow consciousness to adjust naturally to different levels of illumination, while maintaining appreciation for both the bright clarity of direct observation and the subtle beauty of phenomena that operate beyond immediate sensory perception. Let curiosity about electromagnetic radiation and photon behavior serve as a gateway toward broader exploration of physics, mathematics, and the natural world, where patient observation and careful reasoning continue to reveal new connections between theoretical principles and experimental discoveries that expand our understanding of how the universe operates from quantum mechanics to cosmology. The eternal journey of massless photons at light speed provides just one example of how mathematical necessity and physical beauty combine to create the elegant structure that characterizes natural law throughout our observable universe, inviting continued wonder about the remarkable consistency and interconnectedness that enables scientific knowledge to accumulate across generations of researchers seeking deeper understanding of reality itself.